Hi, everyone, and thank you for joining us today at Sustaining Success of Industrial Heat Pumps, a Call to Action webinar. I am Irene Gea Saiz, EU Projects Manager at EHPA, and well, today I'm glad to be your host. This webinar is organized in the context of 3 European projects. I'm talking about Spirit, PUSH2HEAT, and SUSHEAT. But before we talk more about these projects, I wanted to actually start with a question for all of you, which is, where are you all connecting from? And now maybe you should see like pop up in your screen with like the question. If not, feel free to add it in the chat. Actually, me and my colleagues that are here present today, like my colleague Sonia, my colleague Alessia will speak later. We are the 3 of us connecting from Belgium, a very sunny Brussels today. Okay, Germany, Switzerland, Norway, Netherlands, Valencia. New Zealand, okay, like from the other side of the world. That's great. This is amazing. It's great to see that we have an audience from so many different countries and parts. Oh, wow. That's lovely. Okay, I'm just gonna continue, but please keep answering. It's always nice to see that we have such an international audience. And now, yes, I'm gonna start talking about the agenda of the day. Well, right now we are in the introduction. Again, in a few seconds, I will talk about the different projects that are co-organizing this event. And then we will have a speech by my colleague Alessia on the need for policy support for the decarbonization of the European industry. Then Cordin Arpagaus will continue with a presentation on high temperature heat pump technology developments in the European industry. And then we will have the presentation of a success story of industrial heat pump integration from both sides, like from technology provider perspective by Arne Høeg, and then from the end user perspective by Eirik Arnfinn Solberg. And then we will finalize with the Q&A, and we should be done by 11:30 Brussels time. So actually, before I start presenting the projects, some housekeeping rules. If you happen to have a question during the webinar, no problem. You can actually write it on the chat. What I would suggest is that you add the name of the speaker that question is referred to. So for instance, you happen to have a question for me. You just write my name, Irene, and then the question. And then if the question is fast enough, the speaker can answer it on the chat. If not, we can just try to answer it during the Q&A. Then also for everyone, if you need to leave, there's no problem. We are actually recording this webinar, and it will be available as well as with the materials, the presentations in the next days. So do not worry, everything discussed today will be made available very soon. Yes, I'm gonna talk about the different projects organizing this event. So I will start with PUSH2HEAT, in which I am gladly part of. PUSH2HEAT is a Horizon Europe project that started back in October 2022. It has 19 partners from all over Europe, and the coordinator is Tecnalia in Spain. The project aims to address the technical and economic and regulatory barriers that prevent heat upgrading technologies to be widely deployed, and also demonstrates like suitable business models for higher market penetration of these technologies. The project has currently 3 demo sites. One in Weißenbau, Germany, in the paper industry, in which the vapor compression heat pump with piston compressors will be integrated. Then we have a demo in Warcino, Italy, in which it's also in the paper industry. And there will be 2 technologies integrated there. So talking about the vapor compression heat pump with turbo compressors and the absorption heat transformer. And then we have another demo in Antwerp, Belgium, in the chemical industry, in which we will be demonstrating the thermochemical heat transformer. So that's for PUSH2HEAT. For Spirit, well, it's it's a Horizon Europe project. It's actually the sister project from PUSH2HEAT. It will last 42 months. It started back in September 2022, so already a bit more than a year and a half. It has 17 partners from 8 European projects, and the coordinator is TNO. The aim is to enable industrial heat pumps to become the reference climate neutral technology for covering heat demand for temperatures up to 160 degrees by 2030. And it has 3 demo sites in the paper and food sectors. The first demo site, it's prawn processing in Norway. And the technology that will be, let's say, demonstrated, it's the high temperature heat pump, ammonia and pentane in Cascade. The second demo site is in sugar production in Belgium, and the technology to be integrated is the high temperature heat pump, pentane. And then the third demo site is a paper production in Czechia, and the technology to be integrated is the 4-cylinder piston compressor from Spilling Technologies. So last but not least of the projects that are organizing this event, I am talking about SUSHEAT, which will last 48 months. It's the youngest of the projects, I would say. It started in May 2023, and it has 14 partners from different European countries, including affiliated countries of Norway and the UK. And the coordinator is UNED. What it's SUSHEAT about? Well, SUSHEAT will develop a new generation of highly efficient AI-assisted heat upgrading systems to harvest and store renewable energy intensive factory processing needs. And then it will develop and validate a heat upgrading system for reliable, flexible industrial heat, 150 to 250 degrees, focusing on 3 novel technologies. I am talking about an advanced high temperature heat pump, a new thermal energy storage system, a control integration twin system. The concept will be adapted to the demands of the fish oil and dairy in order to validate the system to supply upgraded heat to industry. And then, of course, AI models will adapt to the concept for other stakeholders. So I invite you all, of course, to follow the 3 projects. And then, of course, if you want to check them out already very fast, you can scan the QR code or even click the link. So you can have all the information on all of them. And now, yes, the time has come to let the speakers start speaking. So I'm glad to introduce the first speaker of today, my colleague Alessia Albasto. Alessia graduated with a Master of Arts in EU Public Policy and Administration at Maastricht University. Prior to joining EHPA, Alessia worked at the NGO Positive Money Europe, dealing with central banking and sustainable finance for over 3 years. Previously, she worked at the European Economic and Social Committee and at the European University Institute in Florence. And she joined EHPA in June 2022, covering policy and lobbying work with a specific focus on refrigerants. So Alessia, whenever you're ready, the floor is yours.
Great, thanks, Irene, for the introduction. Very glad to be here today and discuss with you what the EU is doing or not doing on the policy side. Indeed, I am focusing on refrigerants, but recently I have been joining the industrial heat pump group of EHPA. So I have been chairing the group, etc. So that's why I'm here. I'm gaining more and more knowledge on the topic, and of course it's extremely interesting, and it's gaining more and more momentum, as we will see later. I wanted to say a few words about EHPA. We are 24 years old, and we cover 220. We have 220 members across 30 countries. So not only the European Union, but also beyond. So we have a few members from the UK, Turkey, Norway, and Switzerland, based in Brussels, working with the EU institutions, advocating for heat pumps, but also cooperating on at the international level with the Chinese Heat Pump Association, the International Energy Agency, and so on. So now everyone knows heat pumps are mature, let's say, and they're used everywhere, not only in white goods, not only in cars, not only in commercial applications, not only in office buildings, commercial buildings, residential buildings, but also in industries, also in factories and so on. And that's what we're going to talk about today. We know they have reached quite high temperature. It's soon 250 degrees, as my colleague Irene was saying. We have high temperature heat pumps that reach 250 degrees, very high capacity from 100 kilowatt to 50 megawatts. So that's it's pretty great and helps the decarbonizing the industrial sector. Indeed, I was saying, we're gaining more and more momentum. Everyone is talking about it, not only researchers, So there's of course a lot of focus from academics, but there's also policymakers are getting more and more interested in that. The IEA, you can see here, wrote a report on the future of heat pumps, but the World Economic Forum recently published an article as well on decarbonizing the industrial sector in the EU via electrification. And of course, there is a huge focus on industrial heat pumps, on the role that industrial heat pumps can have in decarbonizing the industrial sector. So as we know, industrial heat pumps and residential heat pumps in general, they work with an energy cycle. And what we talk about here is that we need to close the energy cycle, and we need to make sure that waste heat is available in sufficient quantities and it's actually reused in commercial processes it's reused. It's not wasted, as the words say. It's used in new building, as well as in process design. And when we talk to policymakers, whether at national level or at EU level, when it comes to HPA, is that waste heat is taken into consideration and it's finally seen as an opportunity. Let's say we will see later what we mean about that. So, yeah. Let's talk about what the European Union is doing on with regard to industrial heat pumps. Maybe it's worth it to mention first the EU Energy System Integration Strategy, which was published back in July 2020. It was accompanied by a consultation with stakeholders, including, of course, the heat pump industry. They say the strategy says clearly, industrial heat pumps can help decarbonize the low temperature heat supply within industries and can be coupled with waste heat recovery. Yeah, there's a mention to waste heat, of course. And the strategy also acknowledge a few barriers here and there. The lack of information, long payback, training and skills are needed in order to step up the rollout of industrial heat pumps. We talked, as EHP, we talked about training and skills a lot. Talk about, of course, accelerating the rollout of heat pumps. But in order to do that, you need well-trained and skilled installers. Or you need to carry out a few policies on this regard, and one of them is making, of course, this job attractive to the population, to young people, etc. So one of the greatest recognition for heat pumps, including, of course, industrial heat pumps, came in last year with the Net Zero Industry Act. Heat pumps are recognized among the key clean technology to carry out decarbonization in Europe, of course. This was, again, quite a big recognition, which led also to us handing over our heat pump accelerator report to the European Commission themselves. And it's worth to mention as well the EU Energy Efficiency Directive, which instead goes a bit further and focus on the data collection by end-use sectors, including, of course, the industry. It goes to the planning. It says clearly that the member states should remove regulatory barriers for waste heat utilization and etc. So it goes a little bit further, and indeed, it was a step forward in recognizing the opportunity of the wasted opportunity of the waste heat, once again, of the waste heat recovery. The Renewable Energy Directive instead created some kind of legal framework at the EU level, of course, for the development of clean energy all across the EU economy. The EU really wants to be a global leader in developing renewables. Right now, I mean, in 2022, the share of renewables was around 23%. The goal is to bring it to 42.5 by 2030. In the recitals, it's mentioned the opportunity brought by industrial heat pumps. It's mentioned how they can, of course, help decarbonizing the sector, at least when it comes to low temperature below 200 degrees. Member states are invited to promote electrification via industrial heat pumps. And once again, it's said very clearly that waste heat is underused. Its role, of course, in a more wider framework is once again to mainstream renewable energy in industry, but also in Annex 4, it's clearly said that the training should be adapted to the requirements of industrial installations. As we were saying, this is key in order to carry out the rollout of industrial heat pumps. And it's clearly said once again that we should replace fossil fuel use for industrial heating with renewable energy, and of course with industrial heat pumps when it's possible. The directive also mentions that the member states should track the progress done in this regard in specific reports that are then handed over to the European institutions, so that we can see what went wrong, what went right, and we can track the progress for every member state. Now it's time to talk about the F-gas regulation. Let me talk about it for a few minutes, because it's particularly relevant at this stage. You probably know the F-gas regulation has been published on at the end of February and came into force this week on the 11th of March. So indeed, it's quite relevant. Everyone is talking about it. There are few aspects that have been clarified. A few others have not been clarified yet, and will be clarified through implementing or delegated acts throughout this year, probably even before the summer break. We are, as HPA, of course, closely monitoring this developments on the F-gas regulation. What's new in the F-gas regulation? The HSC phase down is steeper than in 2015, and the objective is to reach zero HFC by 2050. You know, the EU has to reach climate neutrality by 2050. So this is should be read in this regard as eliminating HFC is seen as an objective by the EU in the wider framework of climate neutrality, so to say. There are new prohibitions, of course. We will look at them in a minute. There are certification and training requirements extended to HFOs, not only to HFCs, to non-fluorinated alternatives, also known as natural refrigerants. And there are clear rules for customs and competent authorities to crack down on illegal activities. So this is the European Commission really insisted a lot on the specific point throughout the negotiations, and is seen as a novelty in the F-gas regulation, and we're closely monitoring that as well. As HPA, we invited DG Klima to speak at the webinar for our members, during which they introduced the regulation, the main novelties, and so on. Let's look at the bans. The bans are in Annex 4 of the F-gas regulation and Article 8 or Article 9. Now, I think it's particularly relevant, of course, to us to focus on the industrial, on the bans that are related to industrial heat pumps. We can say that industrial heat pumps, high temperature heat pumps, can be both monoblock technology or split technologies. There is a ban in the monoblock. It starts from 2030 and sets other self-contained air conditioning equipment and heat pumps containing F-gases with a GWP 150. So from 2030, there will be a ban on F-gases with a GWP 150 for industrial heat pumps. I say that because if you look at the other bans of this Article 8, they refer to residential heat pumps, hence to small heat pumps. If we look at the split heat pumps and air conditioning devices, the bans that refer two industrial heat pumps. The last two you see in the yellow box. The split system above 12 kilowatt with the F-gases of GWP 750 starting from 2029, and then a ban starting in 2033 for split system above 12 kilowatt with F-gases with the GWP higher than 150. Of course, the negotiations are over by now. The F-gas has been published. More or less, there's a review every 10 years. But we're still monitoring, as I said before, the implementing acts that will go there and clarify specific aspects of the regulation, such as minimum training, certification, and requirements. And we're also monitoring the safety exemptions issue for some of the bands, specifically, especially for the monoblock bands. There are exceptions for in case of safety exemptions, but this needs to be further clarified, considering all the differences there are across member states regarding safety exemptions and the use of specific refrigerants under specific conditions. Then, of course, we have talked about. We have identified a few barriers already. Knowledge and trust, the lack of infrastructure, the fact that complex integration is particularly that the complex integration is as particularly relevant, integrating energy carrier with the key technologies, etc. That's particularly important as well. But what I want to conclude this presentation with is electricity price. We really believe that at this stage, the price ratio between electricity and gas must absolutely come down at this stage. AHPA specifically calls for the price of electricity to be no more than double the price of gas. We support carbon price and policy instruments that in general shield citizens for electricity's price spikes. We need to make sure that for industry and citizens and consumers, heat pumps become a rational choice from the economic point of view, and reduce, of course, the gas price, the electricity and gas price ratio, but also reducing upfront costs, boost financial tools to reduce such upfront cost and make it easier to access loans, green loans, renovation loans, subsidies, and etc. Yeah, indeed. They have identified barriers, but we also offer solutions. And I'm always here to help to answer your questions, whether here during this webinar or beyond the webinar. Once the webinar is over, you can reach out to me to this email address. And yeah, thanks a lot.
Thank you very much, Alessia, for your presentation. Indeed, Alessia, she's always happy to answer questions. So if you have any questions for her, please feel free to also reach out to her directly. It's time that we move on to the next presentation, which is by Cordin Arpagaus. So a brief introduction on Cordin. Cordin is a process engineer with a master's degree from the Swiss Federal Institute of Technology in Zurich. He also holds a master's degree in business administration from the same university in Zurich, doctorate from the same university. He worked several years in industry and in management positions of Swiss companies active in laboratory and process technology. And since April 2015, he is a senior research engineer at the Institute for Energy Systems, the Eastern Switzerland University of Applied Sciences. His research activities focused on thermal energy systems and energy efficiency in industrial processes in particular, high temperature heat pumps and heat pumps with turbo compressors. So yeah, it's a very adequate person to be here today. So please, Gordon, whenever you're ready, the floor is yours.
Thank you very much, Irene. I hope you can hear me well. I have now the control for the slides. Yes, great. So this is a work I would like to present from our team. We are at the Eastern Switzerland University of Applied Science at the Institute for Energy Systems. And we are especially looking at the markets of high temperature heat pumps and the latest developments. So in this presentation, some women engineers will help me through the presentation because it's a very man-dominated research field. So I'll give you some motivation, state-of-the-art, realized examples, go to refrigerants, business models a little bit, economic situation, and a summary and conclusions. So an announcement in next week on Monday, we will have a steam generating heat pump webinar organized by our university. So if you are interested to join, just do it. It will be very comprehensive presentations there. So the motivation for industrial heat pumps or high temperature heat pumps is coming from the energy demand. A lot of energy is required for process heating and divided by the temperature levels. We have seen that before. It's the low temperature range below, let's say, 200 degrees. That is interesting for high temperature heat pumps to upgrade waste heat to higher temperature. For higher temperatures than 200 degrees, there will be some other technologies, some other renewable energies used. So the focus is on that lower part here. So it's around 37% of the process heat. So heat pumps are a key technology to decarbonize industrial process heat. So just as a important fact. So then we have IEA 58, Annex 58, where we participated also as a Swiss university. So there were several countries participating, and we are developing reports, task reports. And the first task one report is about high temperature heat pump technology. So this report is available for downloading, and it has very valuable information, and I will use some of it for today's presentation. I generated this slide here. It is an overview of many heat pump suppliers which are now active in this market. The left graph is the illustration of the temperatures that can be achieved as a function of the heating capacity, and in color the compressor technology. So you can see these products or these machines are providing heat higher than 100 degrees, so up to 280 probably, when we include as well vapor recompression technology, so open cycle heat pumps. So the message here, the market is evolving. I would expect probably 5 new companies every year. So the companies are located in different places with headquarters in Europe. You can see here main companies in Norway or in Germany and some other countries. And for sure, there are others around the world which were not, let's say, participating in this Annex project. Important is the technology readiness level as a measure of the maturity of the technology. And for high temperature heat pumps, we also see such kind of distribution of the products in these technology readiness levels. We can say, okay, readiness level 7, 8, 9. This is very close to commercialization. And here, the heat pump suppliers are pushing their products towards higher TRL level. Here is a table from this Annex report, structured by company name and then by TRL level. And you see on the right, there are several which are already commercialized. So we would expect more and more in the next years. So here we have 23 market available products, 7 prototypes, and 3 in lab small scale prototype stage. And there are other suppliers here on the left, on the right, which also provide industrial and large scale heat pumps. Important for an end user is the operating map. And here we have some of these operating maps illustrated as a function of heat source temperature and heat supply temperature. And you can see there are several products which can provide, let's say, 120-degree heat from a waste heat of 50. So here you have quite an overlap of operating maps, which is an interesting spot and an interesting range for various applications. I have now 2 companies I would like to, or 3, to focus a little bit more. Enerin, we have Arne later on with a presentation. The interesting thing of the HEAT heat pump is that it is working in a Stirling cycle with helium as a refrigerant. So helium has the advantage that it is, let's say, a noble gas with no problems for the environment, let's say, no ODP, no GWP. So this technology is close to market. On the right, you see here a demo, pilot installation in Norway to remove CO2 from biogas. So they need steam. So this machine is producing steam at about 2 bar gauge, 134 degree, and it is now running and in operation. Important is that the machine is isolated. So you see here the isolation for the compressor, and at high temperature, the let's say waste or the radiation can be substantial. So that is an important measure. On the right, you can see some COP data, and here another advantage of this HEAT heat pump. It can achieve very high temperature lifts, the temperature lift between source and sink. So this is data from 21 degree, let's say, source temperature up to 139, so over 120 Kelvin lift, and still the COP is in a range of 1.8 to 1.6, so 1.8 times more efficient than an electrical heater. Then this company is SPH, Sustainable Process Heat in Germany. They are providing a steam generating heat pump called Thermo Booster, and is based on a piston compressor, 4-cylinder, and they have quite modular design, so to fit different heating capacities and also temperatures. The refrigerants can be selected between HFOs, but also hydrocarbon refrigerants like butane or pentane. So this is a heat pump that can generate steam. And here you can see an overview of a laboratory for testing the Thermo Booster. In PUSH2HEAT, which is the European funded project, SPH is also providing a heat pump for an application in the paper industry for the company Felix Schoeller Group in Germany. And you can see here on the right the setup of this 2-stage heat pump, which is designed as a cascade with 2 refrigerants. In the first stage, R515B, and second stage R1233ZDE, so 2 synthetic refrigerants using here piston and screw compressors. The source is the waste heat or the humid, let's say, exhaust air from a dryer, from the paper machine dryer, and it is then upgraded to steam, low pressure steam at 2.2 bar absolute. The capacity over 1 megawatt. So a very interesting setup. What you can see on the left here of the SPH heat pump is the steam condenser, and the steam generator or condenser is from Vaterus, a Finnish company. You can see here the design. So it's a plate and shell heat exchanger where the refrigerant goes in from the right here, and it is condensed and comes out again on the right. And the feed water or the water inlet is from the bottom, and it is heated up and then evaporated to steam. So there is a water level control, and the shell is the steam boiler in this equipment, and it's quite a robust design. So we'll see probably many applications of this plate and shell heat exchanger in the future. So in Europe, there are some realized examples of high temperature heat pumps, and this one is in Ireland, a distillery which is using a heat pump to generate the heat for the distillery. So it goes to 115 degrees. It's from Oilon. Actually, 3 heat pumps are installed, 2 which can go up to 120 degrees, but they also did energy analysis and optimized, let's say, the temperature levels for their processes to increase the efficiency. Capacity also in the 1 megawatt range. Another application from Gallon Counterflow with the Combitherm heat pumps. This is an electric food dryer for pet food. So the heat pumps are used to generate the hot air for the dryer. And here you have 4 heat pumps from Combitherm generating in total, let's say, 3.5 megawatt. Also with a synthetic refrigerant and screw compressors from Bitzer. So using the exhaust air as a source. So a typical application for drying, using that humid exhaust air as a source and upgrading it to higher temperature inlet air for the drying. From the refrigerant point of view, we see a trend towards, let's say, natural refrigerants, where we also would count, for example, also helium. But there are the hydrocarbons, ammonia, water, CO2, and then the HFOs in red, which still have application. And also the next years, there will be several heat pumps using this refrigerant. The HFC need to be replaced probably by HFO refrigerants. So there are some temperature ranges where the refrigerants are most suitable. You can see it here. I think this graph has been presented several times. What is important is that water on the bottom is really the refrigerant for the highest temperature. So we go to steam applications. It could go down to probably 70 degrees, 80 degrees as a starting point. So below 1 bar absolute pressure. Then the compressor or the van has to be vacuum tight or airtight to operate properly. So, but there is still a lack of installed realized examples, and there are some barriers. We have seen these before. This is a result from a survey between among several experts in the value chain, let's say, from planners to manufacturers to industry, also energy service companies. And you see the big bars are fuel price is too low, the gas price is, let's say, too cheap for the electric driven heat pump. Product acceptance is another important barrier. So yeah, the end users need to be convinced that the machines are reliable, and yeah, they need a demonstration that this works. So from adoption, from market adoption with industrial heat pumps, we are still on the left at a very low percentage. Maybe 1 of 100 companies, 1% has an industrial heat pump so far. So there is a big need to push this technology to higher adoption level. So subsidies and funding programs are in place in many countries to push this technology. In blue, you see the heat pump adoption for residential heat pumps in Switzerland. So you see it reached already 65%. So it's over the majority. So this is, let's say, state-of-the-art technology for heating houses. And in industry, there is still a lot of work to do. So business models, we did a survey between or among 16 heat pump manufacturers for high temperature heat pumps. And what you can see is that the customers typically want to purchase the heat pump, which means they want to own their heat pump as an equipment. Energy as a service, maybe heat as a service may be interesting in the future, where there are such concepts, and also leasing could be interesting. But the direct to customer is at the moment the most important business model. Then there are other technologies which are in competition with heat pumps, especially you can see here electric boilers or biomass, biogas, and some other technologies. So this has to be taken into account, especially when evaluating the economic situation. The COP, the efficiency is clear. So there is the relationship between the temperature lift and the COP. So if we would go to very high temperature lifts between sink and then we would reach a COP of 1, which is in principle an electrical heater. So the temperature lift needs to be in a range where we have a benefit of the heat pump. So a COP of 2 or 3, this is what we want to have. So the application needs to be a suitable application for a heat pump. Okay, market attractiveness. This graph shows the relationship between an economic temperature lift and the price ratio of electricity to gas. So it means the lower the price ratio, which means gas is expensive and electricity cheap, then there are higher temperature lifts possible, which are still economic compared to a gas fossil fueled heating system. So it's quite clear, and it just illustrates the relationship. For different countries, in different countries there are different ratios. So in principle, it's possible to place the countries here also on this curve. So it means Scandinavian countries have a very low price ratio, so heat pumps is very attractive technology. But in UK or other countries which have high price ratio, only a temperature lift of maybe 40 or 30 Kelvin is economic. So the goal should be to push this towards the left. Economically wise, we have different input parameters that influence the payback for a heat pump. And here you see a sensitivity analysis, and you see electricity price is important, the temperature lift, so the COP or the application, then the cost factors for planning and integration, and so on. On the other side, okay, the gas price, and also the operating time is an important parameter. It's better to run the heat pump more hours than less. So this is, I think, very clear. The influencing parameters are there. It's just a question of the local situation of that end user, and especially also on the investment costs for the heat pump and the whole project. So from OST, we have generated some free tools for heat pump calculation. Here, an economic calculator. You could download here this Excel file, or also a payback calculator, which gives a country comparison. So maybe it's useful for you to have a first guess of the economic situation. So as a summary, Oh, all together. Okay, here we have many products. We have seen that from the IEA Annex 58 project. Several heat pumps are very close to market and some already commercialized. Application examples, yeah, we have seen some realized examples that generate steam or hot air or pressurized water. The economic situation is depending strongly on the price ratio, but also on the temperature lift. It needs to be a suitable application for a heat pump. Then there are some countries where these conditions are more favorable than in others in Europe. From the business models perspective, purchase is very often seen, but in the future also heat as a service could be attractive. From the refrigerant point of view, we have seen that before. F-gas regulation pushes the refrigerants towards natural refrigerants or refrigerants with very low GWP. So finally, I hope that you have confidence in high temperature heat pump technology and give heat pump technology a try. So at last, I'd like to acknowledge 3 projects in Switzerland here, Decarbs CH, which is about heating and cooling of the Swiss industry. Then Annex 58, we mentioned before, and PUSH2HEAT, the European funded project. So thank you for your attention.
Thank you very much, Corinne, for your presentation. And indeed, let's heat pump technology a try. I think this is a perfect transition for actually our next presentation. Well, as I mentioned when I was presenting the agenda, we will have now the presentation of a success story of industrial heat pump integration. So, I would like to introduce our next speaker, Arne Høeg. Okay, so Arne, he has a master's in process engineering and mechanical design with 26 years of experience in clean tech research and development. Among his many ventures that I have written here, he is CEO, founder, inventor of the single-phase power high temperature helium heat pumps, research and development engineer at 2Circle Industries, focusing on high temperature steam heat pumps, chief technology officer at Sigma Elektrotechnisk and Isenco, leading projects on micro combined heat pump and powered units, and then contributed expertise to Adigo Mechatronics, developing precision agriculture and machine vision systems aimed at reducing, eliminating herbicide use. So Arne, whenever you're ready, the floor is yours.
Thanks. What was this now?
Yeah, you can take control, just
yes,
in the upper tab. If not, let me know and I can pass the slides for you.
Yeah, perfect. Yeah, so this first slide. So thank you for the introduction. So yeah, all those merits, those are previous engagements. So now I'm the CEO and founder of Enerin. So we'll start by introducing the heat pump. Okay, thank you, Corinne, for introducing our heat pump. Yeah, it's a Stirling cycle heat pump using helium, as Corinne said. We can use other gases as well, so it will work with nitrogen with a slight performance penalty, and it will also work with hydrogen with, in fact, a small improvement in performance. So we can generate up to 200 degrees at this point from any heat source temperature, even from below 0. And we have the projects, so like in SUSHEAT to increase the temperature to 250 degrees. Basically, it can probably deliver 250 degrees right now, but we don't have a test rig to test above 200 degrees at this point. So in addition to the temperature lifts that are possible, It's easy to integrate. It doesn't have any, let's say, thermal mass as the traditional vapor compression heat pump has. So when the heat source temperature varies, we don't need to change the pressure in a compressor. We just adapt to automatically in the process to the new temperatures. So the temperatures can vary on both the source and the heat sink sides by tens of degrees without affecting the performance other than the electricity consumption. Let's say basically power in, heat source in, steam out. We can also deliver, let's say, hot water directly or thermal oil instead. So it's one process, one refrigerant for any temperature range. And that means that if the customer has, let's say, 170-degree hot water circuit or an 8-bar steam system, if in the future they find that they can lower the steam pressure or the temperature, the heat pump will still be able to deliver the same amount of heat, but with a better efficiency. So no need to wait for the next redesign of the plant to go for heat pump. Just add the heat pump and do the changes in the plant later. So here you can see the first installation from the outside. So this is a biogas facility. You can see the anaerobic digesters in the back and the CO2 capturing system in the middle and the heat pump in the container here. So it's possible to deliver for brownfield applications and installations. I won't spend too much time on this one other than say it's a piston compressor with integrated heat exchangers. So very compact design. And here, as Corinne also mentioned, this is a Wachterus steam generator, in this case heated by a hot water circuit from the heat pump. And we have tested, like he also said, up to 200 degrees on the water temperature out of the heat pump. So that's the highest temperature that these pipes can accept in this installation. But the new test rig that is built at KTH in Stockholm will be able to handle up to 250 degrees on the hot side. So then we'll be able to map the performance up to those temperatures. I'll also add an additional benefit when replacing oil and gas with heat pumps. So one thing is the factor of maybe 3 in energy consumption, but the other is that you also reduce the strain on the energy system. So many plants are constrained by the cooling system or the waste heat circuits. So probably in the summer, the capacity can be affected by those constraints. So adding a heat pump, you not only save energy, but you reduce the strain on older and systems in the plant, and you will also be, let's say, insured against high gas prices. Going into, let's say, the efficiency. So we have the COP, obviously, but looking at the Carnot efficiency, we see that especially at very high temperature ratio in kelvins, the Högtemp heat pumps will be more efficient than other heat pumps. So that's especially interesting for the next frontier with the very high temperatures. So summing up the heat pump technology from our side is that the Högtemp will be the best solution for the very high temperatures and for the high temperature lifts, but also for varying conditions. So that's very important. Not all companies and all plants have stable temperatures and energy consumption. So if the conditions vary, this type of heat pump will also be a very good alternative in the low range with the higher COPs. So at Pelagia Moray, we will be installing 1.6 megawatt of högtemp heat pumps. So the first step is 400 kilowatts this spring, and we'll then build out to 1.6 eventually in this case. So when integrating this heat pump into the plant, we looked at the energy flows and everything. We have a very good tool to monitor energy use. So we looked at this energy demand here, fluctuates quite a lot, and also in the ramp-ups, all the different flows and machines are turned on so that nothing is very stable. Also, the heat sources are at different temperatures and levels, and we found that it's, the average Carnot efficiency will typically be 50 to 60%. So we had to do a pinch analysis. We do a dynamic pinch analysis so that we can watch how the pinch point fluctuates from minute to minute. So we have built a digital twin of the plant, and then we can see how best to integrate the heat pump. Also, we see here we have the temperatures at Pelagia. So we have the heat sink temperature, 8 bars or 5 bars. So that's the typical variation of the steam pressure. And the heat source can be anywhere between 10 and 80 degrees for waste heat, but also seawater is a possibility as a heat source. And then we see these 3 lines here are the typical operating points that we will look at. So for a low heat source, high pressure, and then lower pressure steam, but still a low temperature heat source. And then we have the high heat source and low steam pressure. That means we will typically be at a COP of 1.8, but at times we can do 2.5. And then between or at ramp up, we can utilize maybe cheap electricity to also use the low COP values there. So this is more or less what it will look like. It's then a 12-cylinder heat pump, and it will be something like this. And then the next one will be besides it in the machine room. No oil degradation, because if you look at this schematic of the heat pump, we only have oil lubrication for the mechanical components here, and we have a very, very efficient piston rod seal that keeps the oil below the piston rod seal, and we have a completely dry process in the heat exchangers and everything. The capacity is from the smallest one, 200 kilowatts. The largest module is 1 megawatt. So the heat pump that we will install here at Pelagia will have a maximum heating capacity of 1 megawatt. So it's very silent. I mean, it's no problem to speak in a normal voice besides the heat pump when it's running at full power. You have, let's say, this is, I mean, it's not a high-tech sound measurements, but 79 decibel here, and you don't really hear the heat pump, because what you hear is the fans from the frequency converters and the pumps and everything, other noises in the machine rooms. So other than that, it's approximately 1 million euros per megawatt. That's the standard price. And then we have operating contracts, and they start at, well, it's approximately 1 euro cent per kilowatt hour saved energy. So that's then more or less the typical level. That means that in most markets with high gas prices and low electricity prices, or if you're able to utilize storage so that you can use the cheap, abundant renewable energy, then a 3-year payback should be entirely possible. So yeah, I just say that to sum up, well, we have the technology to decarbonize the industry today. I think we meet most of these barriers that people see. There was a question, but it was, let's see. So, and Elin, we are 10 people at the moment. We are interviewing 2 more people now to hopefully start before the summer. So there will be 12 employees, and we plan to recruit more people later in this year. And the heat pump is a single state, so it's all ideal gas. It's one stage regardless of the temperature lift. So that's why we can achieve a very, very good Carnot efficiency at high temperature lifts. It's because the heat pump will do everything in one step. I mean, in the lab, we have also tested up to 600-degree temperature lift, obviously on a small prototype, but it's yeah. Any more questions? It's not similar to Heaton at all, because Heaton is a traditional vapor compression company. They use a compressor to compress HFO or hydrocarbon, so it's pretty standard. But we make Stirling cycle heat pumps. We make the heat pumps ourselves, the whole thing, with sub-suppliers. So we use automotive industry suppliers from Germany and the UK, Sweden. We also use a lot of industry supplier, engine and industry suppliers in Finland and so on. Comparing to Olvondo, well, Olvondo makes my old design. So I designed that heat pump back in single phase power in 2011. So it's similar technology, but we've targeted all the limitations of that design. So that design was limited in the high temperature, and we also succeeded in increasing the COP. But otherwise, it's more or less the same process as they use. And as for capacity, well, we're installing 2 heat pumps this spring. So one at Pelage, one at GE Healthcare. So that's a pharmaceutical plant. I think we can have the capacity to make like 10 heat pumps for 2025, but we are rapidly able to scale as we use automotive suppliers and so on. So we can really scale quickly to meet the market demand. ECOP, I know them. They are a very nice company, different technology. They use the Joule process, also using noble gases. Very nice. Wish them all the best. Completely different process.
Thank you, Arne, for the presentation and also for answering all these questions in the chat. That was amazing. But now it's time that we have to move on with our next presentation. Well, the last presentation of today, actually. So I would like to introduce our last, but of course not least, of our speakers. I'm talking about Eirik Anfinsen Solberg. Eirik is a technical manager at Pelagia, where he leads a diverse range of energy-efficient projects aimed at reducing cost and emissions across their factories. With a focus on innovation, Eirik specializes in implementing cutting-edge technologies such as steam-generating heat pumps to optimize energy usage and minimize environmental impact in industrial settings. Drawing from extensive experience as a product developer, Eirik has successfully navigated projects in sectors including oil and gas, aquaculture, and fisheries. His expertise spans both hardware and software development, allowing him to deliver tailored solutions that address the specific challenges faced by each industry. So whenever you're ready, Eirik, it's your time to shine.
Okay, thank you very much for the introduction. Yes, as Irene mentioned, I work at Pelagia, and we are working very hard to reduce the energy input of our factories. A little bit about Pelagia. We are a leading producer of pelagic fish, which is mackerel, herring, blue whiting, and other. We have headquarters in Bergen, Norway, where I'm located now. And we have around 25 production facilities, mainly in Norway and UK, but also presence in Denmark and Ukraine. In Norway, we have a yearly CO2 emission of around 52,000 tons. So that we would like to reduce. Our key products are food for a human. That could be fillets or frozen fish. We have a feed department that produces fish oil and fish meal that goes into animal feed and mostly to the salmon industry. And we also have a health department which produces omega-3 oil for pharmaceutical and nutritional industries. Since we are a big energy consumer, at least the feed industry uses the most fossil fuels. We have continuous and increasing focus on energy in Pelagia. We also have different factories of different age, so we are doing we have different things we can do, like optimizing the operation, cleaning routines for equipment. These are easy things to do. And we also have different type of fuels and energy we use at our different facilities. So we need different strategies at every plant. We also try to exchange the experience between our factories, and also like we talk about today, contribute to innovation and also facilitate for industry trials at our plants. So we are contributor in several projects on heat pumps and energy, both in Norway but also EU project like the SUSHEAT that we are here on behalf of today. Let's see. Just a quick overview of a general fish meal factory. We have the whole point of the factory is to take in raw material, fish, and separate it into solids. That would be the meal, oil, and water. So we're trying to remove the water and sell the products, which is meal and oil. And this demands a lot of energy, mainly in the form of heat. So the biggest consumers here would be the cooker and the two dryers. We have one pre-dryer that uses steam and a final dryer which uses hot air. We also have this waste heat evaporators, but they operate on waste heat from the dryer steam. So since we have a lot of waste heat from many of our processes in the form of steam from our dryers. We have surplus steam from our dryers. This will be used into the heat pump system, and we also have dirty condensate from cookers and dryers that both dirty and or from the dryers and waste heat evaporators. I mean, this will also be used into the heat pump system. So we are at Måløy. We are currently installing systems from two different contractors. That is Aneo and Enerin that Arne presented just now. So the reason that we have two different vendors is that they are different system with different temperature lifts. So we use the kind of correct technology for the energy lifts that we need. So the smaller energy lifts, we will use the Aneo system, and for the larger energy lifts, we will use the Enerin to get the best COP that we can in total. So the way it works is that we have dirty steam from the dryer. That is steam from the fish that has evaporated. We take this into a heat exchanger. That is actually a steam heat exchanger. So we get out clean steam on this secondary side. This is a vacuum steam at around 80 degrees or so. And this merges with the steam produced at the ammonia heat pump here. This steam is generated from condensate of around 85 degrees. So this merges together and goes into 6 big MVR fans and is compressed to about 2.5 bar Gs, which we can route to our consumers that are the cookers. These are the only consumers that use steam at this low pressure. So that is why we route steam to them. In addition, we have the steam dryers, but they use steam at higher pressures. This is where the Enerin heat pump comes in. This use actually the same condensate stream as Aneo, but since it has a very high temperature lift, we're able to take the rest of the condensate after Aneo's heat pump that will have around 30 to 40 degrees and lift it up to 5 to 9 bars that we can use in our dryers. So in combination, we are able to extract the most heat possible from our waste heat. We are actually currently finishing the installation of the whole system, and just after Easter, we will start testing and commissioning of the system. So the investments we made into the system, including the energy and the factory and the room where the machine room and everything is around 6.5 million euros. We will have a total reduction in energy input of about 15% and a CO2 reduction of emission of around 3,500 tons yearly. That is around 23% of the Måløy factory. And the return on investment we expect to be less than 7 years, but this will depend on both electricity prices and cost of CO2 emissions in the years to come. So in the future, like Arne said, we are starting with one Enerin heat pump, but we have the space to build out with several more if it turns out to be a success. And then we will be able to produce steam for more of our dryers. we do not have enough waste heat or we do not have, we're basically using all our waste heat today. So we will have to introduce seawater as a heat source for the next heat pumps. And together with the SUSHEAT, they are using our factory data that we have provided them with, and they are looking into simulation of control systems and machine learning algorithms to optimize the production in our factory. In SUSHEAT, there's also looking into storage of energy. Since our factories are like Arne showed in the graphs, we don't have a consistent what you call stable energy usage. We have to use the energy when the fish arrives. So we are ramping up and shutting down production many times a year. And that would be a very good place to test out thermal energy storage as well. The vapor recompression in the Aneo system is the pillar fans. And the ammonia heat pump is a SLS heat pump, as answer to a question. So we are very excited about starting up this system after Easter, and we hope it will be a success, obviously. Yes, thank you.
Thank you very much, Eirik. And of course, we also hope it will be a success. So now, before we start with a very brief Q&A actually, because we are like running out of time already practically. I wanted to ask you all, what's your energy level as of now? So I'm just gonna launch a poll, and of course, you're very much welcome to just share with us how are you feeling. I see the energy level is pretty high. That's great. I mean, weekend is coming very soon, so I understand. But okay, so I think we can start with some, actually, as I said, we don't really have that much time for questions, but I think it's a good opportunity since we are all here. I wanted to start with a question for Cordin. Actually, I wanted to ask you again, you briefly mentioned barriers, I know, but it's always interesting to always hear what are the main barriers, but also the main drivers for the market introduction of high temperature heat pumps.
Yeah, this is a very good question. We have seen the barriers in several presentations. Once we have seen this about prices of gas and electricity, then the reliability and availability of such heat pumps in realized examples. Then we have seen the training and the skills of the installers. So we need a lot of people that are trained on these systems. And the benefits, it's all about, let's say, decarbonization, electrification, saving energy, CO2 reduction. This I would mention here.
Lovely, thank you. And then, of course, this is a bit linked. Eirik just was presenting his perspective, Pelagia's perspective as an user. So what are the main challenges for Pelagia in this case to actually implement heat pumps?
Yes, the main challenges, because we have factories at different locations, obviously, one challenge is that it's quite new technology, so we are taking a risk of implementing it and a big cost in doing so. But one of the main challenges with implementing it in other factories would be the access to electricity, basically, because Måløy is the one factory where we had quite easy to get electricity and didn't have to build out the major electricity lines to get it there. So that would be a big challenge in other locations we have.
And then, even though there might be a challenge in other locations, will Pelagia install heat pumps in more factories, do you think?
Yes, we are looking into to installing more places also. So, but everything depends on the outcome of this project, obviously. So if it's good business for us and it is working without a lot of maintenance, then we will obviously consider it in all our factories if we are able to get electricity. But we are looking into many different solutions also to reduce CO2 emissions, and heat pumps is an important part of it.
Definitely, of course, we wish you success on the project. I have also a question for Arne. I know you asked, you answered many questions, Arne, during your presentation, but I am not sure, or at least in my case, it was, I didn't really grasp what was the delivery time of the system.
Yeah, it's at the moment it's just above 1 year. We are working to get that down, but there are a lot of long lead items at this stage.
Okay. And then actually I have like questions from the audience that were asked very much at the beginning, but I thought it could be interesting that they were asking, well, I think might be a bit more for Cordin, but if maybe some, like you also have some ideas. They were asking what was the prediction, well, what was your prediction on which high temperature heat pumps or compressors would be used the most?
Well,
here we cannot give I think a clear answer. So there are 3 or 4, let's say, compressor technologies which all are suitable for high temperatures. So the pistons have advantage that you can separate the oil from the gas phase, let's say. Then screw compressors are also there for high temperatures. Then the turbo without oil. So it's not so easy to say. So I think every manufacturer has their competence to design these compressors for high temperatures, but there's some work to do.
Completely understandable.
Could I add? I think many of the companies that we have talked to and have heard all say that the market is so big that it's the main challenge is to scale quickly enough. So there will be room for all manufacturers, I think.
And then I think we have another question, like again from the start of the webinar, that it was like right away it said question to all. So I'm just going to read it out loud. It said, what are the industrial applications? Well, what will be the first, in your opinion, the first industrial applications that will really adopt heat pumps, in the sense that what would be like the industries that are more likely to integrate these technologies?
I can answer. So the food industry, we have seen it several times. And then in the food industry, this, for example, drying applications or steam generation applications, principle producing low pressure steam or hot air as a medium or hot pressurized water, and maybe not the highest temperature at the beginning. So yeah, food industry, there are many applications. Then we have seen paper industry, chemical industry.
A bit of everything, I see. Okay, I think I'm just going to ask one more question because I think it's interesting. It's again on barriers. Like it's mentioned that one of the main barriers identified in another case was the access to electricity. Eirik, you mentioned it, but I wanted to ask the perspective on all speakers about this barrier.
I could.
So
yeah. Okay.
I think it's very important. So the access to electricity is needed, and this means a lot of investment into new electricity networks, grids, and so on. And this has to be taken into account in the economic calculations as well. And it's an additional cost factor for the whole project. I'm not so sure how much this is in a percentage, let's say. So if you look at the heat pump equipment as a big part, how much of it additionally would be for the electricity connection? I would assume maybe 20-30% additional costs, or even more.
Yeah, sorry. We did a calculation on the available data on let's say the varying heat sources for industrial process heat, and a significant share is already electric. So replacing the electric boilers with heat pump, that reduces the electricity consumption, and then adding the heat pumps to replace gas and oil and coal, then that increases again, but the net electricity use increase should be more like 15% or so. It's not really much. So and then everyone wants to quit oil and gas, and that means that the heat pump will then use less electricity than direct electrical heating. And it's also possible, as Agora Energiewende also stated now, that combining the heat pump with high temperature energy storage, then the heat pumps can run when there is abundant electricity from solar and wind.
Okay. Well, thank you very much. Unfortunately, we are running out of time. We don't really have more time for questions. But then again, if people from the audience have questions, you can always direct it to the speakers directly. But again, before actually we close the webinar, I wanted to invite everyone to, if you want to know more about the projects that I have mentioned at the beginning and that have been mentioned during the presentations as well, because SUSHEAT and PUSH2HEAT have been presented, I invite you all to scan the QR code or click the link and follow us on social media, check our websites, everything. Many things are happening now. So I think it's a very, very interesting, well, there are 3 very interesting projects. Then, of course, I have to talk about EHPA, since I am an EU projects manager here. But please, if you want to see more events like this, I invite you all to follow us. We are on LinkedIn, X, YouTube. You can subscribe to our newsletters, but you can do that by scanning this QR code. And then now, yes, I want to thank all the speakers that were here today for joining us and taking the time, and of course giving such interesting presentations. I hope all the inputs were super valuable for all of you attendees. Then again, we will share presentations and we will share the recording in the next day, so do not worry, information will be coming your way. And then again, also I want to thank my colleague Sonia helping us today in the back end. She's in the same room as me. Yeah, thank you very much, everyone. And I want to wish you all a lovely day. And I hope lots of sun as well, like in Brussels. So see you soon in another webinar.